Before going forward, let's back up a bit and ask what we've done so far in this chapter. We started by describing the whole story of Easter Island, how it was discovered, and the theories that may explain what may have happened on the island. Then we proposed a model based on the Lutka-Volterra predator-prey model, where islanders are predators and island is the prey, and we have seen the whole mathematics around it. But now it's time to put the two together and ask ourselves, are we able to reconstruct history with our model? So to do that, let's just have a small quiz. So let's consider 5 combinations of S, the stock of resources, and L, the stock of population, represented by these letters A, B, C, D, and E. And just ask ourselves which letter may correspond to which period or which event on the island. So 1 is Polynesians set foot on Easter Island. 2, the Polynesian reaches the population reaches its maximum. 3, the forest has disappeared. And 4, James Cook visits Easter Island. Think about it, and you can go on the website and answer it on quiz number 4. All right, time's up. So, Polynesians set foot on Easter Island. Where is that? Well, this should not be too difficult, since we already said that the Virgin Island equilibrium is here when S is equal to K and L equals to 0. So what's the best letter to describe this event? Well, probably A. So A is essentially the first boat of Polynesians that reach Easter Island. Now, number 2, the population reaches its maximum. Well, now I'm being nice with you. I put them all in order. So where is the population going? Well, we can start at A and then ask ourselves, in that quadrant, where are we going? Well, follow the arrows. So we should be going downward. Why? Because people start exploiting resources, but to the right because the population starts to increase. And so as the population increases, then the pressure on stock starts to increase, and it should decrease. So it looks like we should be reaching the letter D, which is the letter that's closer to the highest population, and which is about halfway in terms of resources. So probably that the population reaches its maximum at somewhere around D. The forest has disappeared. That shouldn't be too difficult too. Let's continue to look at what may have happened on the island. So we are here, and now there's a lot of islanders that harvest the forests really quickly. So the stock of forest really starts dwindling, and as it does, then the population now is unable to sustain itself because we are below this blue line, and the population starts decreasing. So probably we reach this low point at E, where, well, here it looks like we still have some forest, but that's really a low point for the stock of resource. You can still imagine that we have some grass, and we can still do something on the island, but it's very poorly sustained in terms of resources. So probably the forest has disappeared at E. And then that's close to when James Cook visits the island, because then the populations continue to crash and crash and crash. And when James Cook arrives, then the population is probably much, much lower than it used to be when it was at its peak, and probably when people were building moai and being very prosperous. So probably James Cook arrived at letter C, or any other explorer, or De La Pérouse, for instance. And B was just to fool you up, to make it not so easy. All right, I hope it was not too difficult. So there seems to be a way for historical events to match the dynamics of the island. But before going further, some questions still remain around the convergence. So what does it actually look like? Or more specifically, we can ask questions such as, if we start, say, close to the sustained island, are we going to converge toward the sustained island? Or maybe is it going to spiral out of control or go to the collapsed island or the virgin island state? And will we actually see a spiral around the sustained island, or is it going to be, for instance, this way, for instance? So it's not perfectly clear. And to do this, we must study the stability around the sustained steady state. I explained in detail how to do that in the lecture notes. However, it's quite mathematically involved, and it goes quite beyond the scope of this class. Let me just briefly tell you in words how to answer these questions, and if you're interested, then you can dig deeper into the class notes. So what we have to do is actually take a first order approximation of S dot and L dot, so the dynamic of the stock of nature and the population around the sustained island. So first order approximation means that we take the first derivative of each of them with respect to all the variables. So it gives us what we call a Jacobian matrix of the system. But obviously both dynamics are dependent on each other. So what we do is we take the eigenvalues of this Jacobian matrix, which is in a sense isolating each system in its own way. So it allows us to study each of them independently and then learn something about what's happening. So several things can happen. So both eigenvalues can be either both positive, both negative, or one positive, one negative. And they can have real parts or imaginary parts as well, so they can be complex. So if both real parts of the eigenvalues are negative, then this tells us that the system will be stable around the sustained island, meaning that we're going to converge back to the sustained island if we diverge from it. And this is in fact what we find. We find this because there's negative feedback in the predator-prey interaction. Why? Because more prey breed more predators, but more predators eat prey and decrease the population of prey. So we see that there's always this race between the number of, so the island stock and the population of people, which makes, in the end, the system quite stable. So this is what happens in nature. So there's always this lynx population that grows or the hare population that grows, but there's never one of the two populations that go completely extinct. So this is self-regulating. And finally, the question we ask is, are we going to see cycles or spirals around the sustained island or not? So it looks like it from the drawings, the arrows that we've drawn, but it actually depends specifically on the value of the parameter. In the note, we see that this happens if R is small, so if there is slow regeneration of natural resources, if D minus B is small, so if starving islanders that don't have any harvest do not die too quickly and still continue to harvest a lot. And finally, if alpha beta phi is large, alpha many islanders are farming, they like food, beta they are effective at it, and phi this farming boosts their population growth. So is that what happened on the island? Well, probably cycles did happen on Easter Island, specifically since nature did reproduce quite slowly because palm trees don't grow too fast. And this might explain why we saw these large construction, which might have occurred because of a large population in the past with large nature to support it. So with stable, sustained island, steady state, and cycles, this is how convergence would look like. A slow spiral around the steady state, Of course, there's a glaring problem with this version of the model. It's that nature never ends up disappearing. It regenerates as the population goes to very low levels. But on Easter Island, we know that actually the forest did disappear because we can't see it around today. So we infer that it must have gone to zero at some point. But as we already mentioned, it would be possible in principle to amend the model in such a way that nature could not generate below some threshold. And actually, that's the version that we're going to see next. But just before that, let's just look at how the authors actually calibrated the model. By calibration, we mean that they did find out the best parameters and initial conditions of state variables that fit the facts that were observed on the island and by archaeologists.